Dr.A.SRIDEVI, Professor in Department of Electronics and Communication Engineering, M.KUMARASAMY College of Engineering. So today we are going to see design of FIR filter using windowing technique. So the given problem, let us take a given problem, design an FIR low pass filter for the following specifications with order capital N is equal to 5 using Hanning window. So the given specification is HD of e power j omega is equal to e power minus j 2 omega, and the cutoff frequency is from minus pi by 3 to plus pi by 3 because they have given mod. So it is from minus pi by 3 to plus pi by 3 and 0 otherwise. From this given specification, I have identified that the response is Gaussian and it is realizable. And the order of the filter is 5. So first step we are going to do is we are going to find the infinite impulse sequence. That is step 1 is HD of n we have to find using inverse Fourier transformation. So step 1 is I am going to find small HD of n using inverse Fourier transformation. So what is the formula for inverse Fourier transformation? HD of n is equal to 1 by 2 pi integral. So here in this digital it will start from minus pi to plus pi HD of e power j omega into e power j omega n into d omega. So now substitute the value of HD of e power j omega, that is 1 by 2 pi. The given specification as the cutoff frequency minus pi by 3 to plus pi by 3. HD of e power minus 2 omega into e power j omega n into d omega. Now I can further simplify 1 by 2 pi integral minus pi by 3 to plus pi by 3 e power j, I can take it commonly, omega n minus 2 into d omega. Now we are going to integrate this with respect to omega. So that is equal to 1 by 2 pi. So e power j omega n minus 2 divided by j into n minus 2. The upper limit is pi by 3, lower limit is minus pi by 3. Further, I can substitute the value of your, that is 1 by 2 pi. I can further do a small modification. I can bring this pi n minus 2 outside and I can bring this 2 inside. So e power j omega n minus 2, okay, divided by 2j minus pi by 3 to plus pi by 3. Okay. So next one, let me substitute the upper and lower limit. 1 divided by pi into n minus 2, open the bracket, e power j omega value upper limit is pi by 3 n minus 2 minus e power lower limit value is minus pi by 3 into n minus 2 divided by 2j, close the bracket. So that is equal to 1 by pi n minus 2. So can I write this term? This is similar to a formula sin theta is equal to e power j theta minus e power minus j theta divided by 2j. Okay, so I can write this term as sine pi by 3 n minus 2. Okay, all of you. So further I can simplify. It is sine pi by 3 n minus 2 whole divided by pi into n minus 2. So this is the value of small hd of n. Okay, but when you go for n not equal to 2, why? Because if I put n is equal to 2 here in the upper term, this will be 0, this will be 0. So I cannot use this particular value for small n is equal to 2. So when small n is equal to 2, I have to apply L'Hospital's rule. What does that L'Hospital's rule mean? When limit theta tends to 0, sine theta by theta is equal to 1. This is the formula for L'Hospital's rule formula. So I am using this thing and I am getting the value for small n is equal to 2. For small n is equal to 2, sine pi n minus 2 divided by pi n minus 2. So I can write only 1 by 3. So this is my first step answer. So in the second step, what we are going to do is step 2. We are going to find the values of hd of n for capital N is varying from 0, 1, 2, 3, etc. Okay, when small n is equal to 0, 1, 2, 3, etc. till n minus 1. Okay, ba? So why we are taking 0, 1, 2, 3, etc. Because this is a Gaussian filter. Given specification is a Gaussian. So your small n will vary from 0, etc. till capital N minus 1. Let me put a table. N versus hd of n. So small n will take the value 0, 1, 2, 3 and 4. So I need to find the values. So for finding the values, since this is a Gaussian filter, by symmetric condition, it uses symmetricity. Okay, a symmetric condition, my hd of 0 will be equal to hd of 4. That is, you know already symmetric condition is h of n is equal to h of capital N minus 1 minus n. Using this condition, I can write hd of 0 is equal to hd of 4. So let me use the formula, above formula, and get the values for hd of 0 equal to hd of 4. From step 1, what is the formula we have got for hd of n? It is sine pi by 3 n minus 2 divided by pi into n minus 2. Okay, so this is the formula. So now I am going to substitute small n is equal to 4. So hd of 4 is equal to sine pi by 3 into 4 minus 2 divided by pi into 4 minus 2. So that is equal to hd of 4 is equal to, using calculator I can find the value of this HD of pi by 3 sine. So I am getting a value as 0.1378. Okay. So enter this value 0.1378 here and 0.1378. So when small n is equal to 3, okay, HD of 3 by symmetric condition, HD of 3 will be equal to HD of 1. So that is equal to, substitute it here, sine pi by 3, n is 3 minus 2 divided by pi into 3 minus 2. So it will be sine pi by 3 divided by pi. The answer I am getting here for this value is 0.2756. Okay. So it is 0.2756. 0.2756. Already for n is equal to 2, we have got the value 1 by 3, that is equal to 0.33. So now I have got the infinite impulse sequence. Step 2. Next we will go with the step 3. So in step 3, I have to select the window. So what is the given window? The given window is Hanning window. Window also has two formulas, Cauchy and non-Cauchy. So if I take the window formula W, Hn of n is equal to 0.5 minus 0.5 cos of 2 pi n divided by capital N. Okay, so this is the formula for your Hanning n minus 1. This is the formula for Hanning window. So now you are going to find values for this particular window. So again you put a table here. N, small n will vary from 0, 1, 2, 3 and 4. I am going to find the value of the Hanning window. Okay. So by symmetric condition we can know the Hanning window of W of 0 will be equal to W4. Okay, even I can write W also. So let me substitute 4 in this formula. So 0.5 minus 0.5 cos of 2 pi into 4 divided by capital N is 5. So 5 minus 1. That is 0.5 minus 0.5 cos of 8 pi by 4. So using calculator, if you find what is this value is equal to 0. So I can write this two values equal to 0. Next, similarly, you substitute small n is equal to 1, that is W Hn of 1 is equal to 3. Okay, ba? So it is 0.5 minus 0.5 cos of 2 pi into 3 divided by 4. So the value using calculator I am getting it as 0.5. So this value is 0.5. This value is 0.5. Okay. So remaining step again W Hn of 2 I have to find, which is the center term. So substitute here 0.5 minus 0.5 cos of 2 pi into 2 divided by 4. So this will be equal to 1. So 1. Now step 3 I have got window sequence values. In step 2 I have got infinite impulse sequence value. In step 3 I have got the window value. So next step is step 4. I want to get the finite filter coefficient. I want to get the finite filter coefficient h of n. How can I get this h of n? H of n can be got by multiplying infinite impulse sequence hd of n into window function w of n. So already this I have got it in step 2. This I have got it in step 3. Okay, wow. Simply you can put a table which will be easy for you to multiply. So n 0, 1, 2, 3, 4. Center value is 2. Your hd of n from step 2. What is the value in step 2? I have got 0.1378, 0.1378. Here it is 0.2756, 0.2756. This value is 0.33. In step 3, I have got the window function using Hanning window. What is the value? So this is 0, 0, this is 0.5, this is 0.5, and this is 1. So your finite filter coefficient. So this FIR, usually FIR filter will be Gaussian. So FIR filter coefficient, that is nothing but Gaussian. H of n is equal to hd of n into w of n. Okay, into. So directly you can multiply. This is 0. Multiplying this 2, I am getting a value of 0.1378. So multiplying these two values, I am getting 0.33. Here 0.1378. 0 with this value is 0. Now I have got a filter coefficient. So this is my filter coefficient. So what is my filter coefficient? So hd of n is my filter coefficient. In the problem, they have asked you to design a FIR filter. So whenever they are asking, you can either find the transfer function of a filter. So transfer function of the filter is denoted as h of z. The frequency response, if I need to find, means I have to go for h of e power j omega. Depending upon the problem, either you can go for h of z or h of e power j omega. So let me go with the next step. So in step, this is step 4 is over. So step 5. Step 5, I am going to find the digital FIR filter transfer function. Okay, h of z. How can I find this h of z? By applying z transformation. I can apply z transformation. I can find the digital transfer function h of z. What is the formula for h of z? It is equal to summation. Your n varies from 0 to capital N minus 1 h of n z power minus n. This is the formula. So I am going to use this formula and I am going to expand this thing. So h of z is equal to summation, small n varies from 0 to capital N is 5. So 5 minus 1 is 4. H of n into z power minus n. So now expand the summation by substituting small value of n, h of 0 z power 0 plus h of 1 z power minus 1 plus h of 2 z power minus 2 plus h of 3 z power minus 3 plus h of 4 z power minus 4. Now you substitute the value of h of 0, 1, 2, 3, etc. Step 4, I got this value, no, h of n. This values I am going to substitute. So what is the value of h of 0? H of 0 is 0 into plus h of 1 value I am getting is 0.1378 z power minus 1 plus h of 2 value is 0.33 z power minus 2 plus h of 3 value is 0.1378 z power minus 3 plus 0. Since h of 4 is 0. Now if you see these two terms, the coefficient is common. So I can write like this. Center term first I am writing 0.33 z power minus 2 plus commonly I can take the coefficient 0.1378 z power minus 1 plus z power minus 3. Now this is my h of z equation. Okay. So this is my h of z equation. So this is nothing but my FIR filter equation or my transfer function. Okay. So next step, step 6. If I want to find the FIR frequency response h of e power j omega. Okay, next I want to find this means there are two ways by which you can find h of e power j omega. You can use the Fourier transformation formula. What is the Fourier transformation? H of e power j omega will be equal to summation, small n will vary from 0 to capital N minus 1 h of n e power minus j omega n. You can use this formula or directly from the previous step I have calculated h of z. By the relationship between z transformation and Fourier transformation, this both will be equal by substituting z is equal to e power j omega. Okay. So either you can use this formula and you can expand the summation and get the value, or else from the previous step directly I can write. So let me write. So from the previous step, h of e power j omega is equal to 0.33. Instead of z I have to substitute e power j omega. So e power minus already 2 is there. So j 2 omega plus 0.1378 into e power minus 1 is there. So minus j omega plus e power minus 3 is there. So j 3 omega. Now this is my Fourier transformation frequency response. So why we go for Fourier transformation? In any signal, if I want to find the magnitude and phase, I have to find the Fourier transformation or I have to apply the Fourier transformation. So let me find the magnitude. Magnitude usually mod h of e power j omega. So whenever I need to find the magnitude, okay, yes, I need to find magnitude means I have to take the phase factor outside. So what is the center term phase factor? So h of e power j omega is equal to, I am taking e power minus j 2 omega is the phase factor of a center term. So I am taking outside. So remaining term 0.33. Since when I am taking e power minus j 2 omega, I have to multiply e power j plus 2 omega inside the second term. So 0.1378. So e power minus j omega into e power plus 2 j omega plus e power minus j 3 omega into e power plus j 2 omega. Okay. So that is equal to e power minus j 2 omega inside this bracket 0.33 plus 0.1378. If I simplify the terms, you will be getting e power j omega plus e power minus j omega. Okay. So you know the formula, trigonometric formula, that cos theta is equal to e power j theta plus e power minus j theta divided by 2. Okay, so now I am going to use this formula and simplify that. So my h of e power j omega will be equal to e power minus j 2 omega into 0.33 plus 0.1378 into 2 cos j, that is cos omega. J omega, e power j omega plus e power minus j omega can be written as 2 cos theta. So theta here is omega. So it is equal to e power minus j 2 omega 0.33 plus, when I multiply this, I am getting an answer 0.2756 cos omega. Okay, ba? So now, which is magnitude? The term which is present inside this bracket, no, that is my magnitude. So magnitude mod h of e power j omega is equal to 0.33 plus 0.2756 cos omega. My phase angle is angle h of e power j omega will be equal to, the term which is there here, no, it is minus 2 omega. So this is my magnitude of your FIR filter. This is my phase of your FIR filter. So now we have completely designed an FIR low pass filter for the order capital N is equal to 5 using Hanning window. So this given specification is Gaussian. So we have used directly the Gaussian formula of window and we have got. If it is a non-Gaussian, then what we have to do? We have to convert to Gaussian and then we have to go for the simplification. Thank you.